Hello and welcome to my video, lesson 5.3b on de Broglie's wavelength or de Broglie's wavelength. So essentially this entire unit, chapter 5 or whatever, unit 5, was light as a particle. And so if we can say that light can act in packets and particles, or like a particle, like a photon, maybe particles can act like waves. Because if a photon can have momentum, as we saw with Compton scattering, then maybe a photon, so therefore if photons can have momentum, maybe we can reverse this and say that electrons or protons or alpha particles or any other particles can have a wavelength. And so basically what we're doing here is we're coming up with these two ideas, basically that for a particle, the momentum is like this, rho mv, and then for a photon, or a wave, it's h over lambda. And so these are the two different versions of momentum. And so if we put those two together, we get this formula, which is our de Broglie wavelength formula, or de Broglie's wavelength formula. So we can rearrange this however we wish, but the interesting thing is if we rearrange this for lambda, we can figure out the wavelength of any particle with mass. And so some particles are more realistic than others. If we talk about a human being, we're like in the order of 100 kilograms or more, in that ballpark, or I guess 60 to 100 kilograms. And so that size is a little bit too big, not just a little bit too big, way too big, for it to be a reasonable wavelength. And so usually when we're talking about this, we're talking about really small things. And this first started with electrons, because with electrons, we can shoot them into a diffraction grating. And it turns out that when you shoot electrons in a diffraction grating, they will actually have an interference pattern, just like the waves of light. And so you see that interference pattern with the central node and then all these antinodes or whatever around, and you see that pattern occur even with electrons. And so because of that, we can see that electrons also act like waves sometimes. And so it's actually funny because it depends on if you're looking at them. If you're looking at the electrons, then because we're looking at them, we're measuring them, I should say. Because we're measuring them, we're imparting some information to them, and therefore we're changing the story. We're changing the experiment. And so electrons behave differently in different circumstances. It's because they're particles and waves, just like light is a particle and a wave. Yeah, so we're looking at the wavelength of an electron traveling at this speed. So what we're going to do is just simply use this formula as is. Now, this formula is not given in your formula sheet. What's given is these two formulas, which you then put together into this formula, which then you can rearrange for all these different types of questions. Anyways, we've already done the rearranging, so let's go ahead and solve this. So then we get this value. So 1.68 times 10 to the negative 10 meters. Which I believe is an angstrom. Or you could say 0.168 nanometers. If you want to think about it, nanometers, that's kind of nice because you can kind of compare that to the wavelength of light, and it's actually not that far off. It's a little bit smaller, so smaller wavelength means higher energy if we're talking about light, but it's interesting that it's kind of in the ballpark of what light is. Okay, here it says a proton has a wavelength of that. How fast is it traveling? So what we're going to do is start off with our two things being equivalent to momentums. Then we're going to look for the speed. So we're going to rearrange that for speed. And so we're going to plug it back into our calculator. All right, and we can get that value, and we get this. So it's 1, 2, 3, 4, 5, 6. 1.21 times 10 to the 6 meters per second. All right. One last question to try. Same setup as before. It's looking for the mass this time. And so what we're going to do is we're going to set this up. mv equals h over lambda. And we're going to solve for the mass. So we're going to rearrange that. So it's mass equals h over lambda v. And so again, we just need to plug it into our calculator. There you go. So that is our answer there, which is 1.03 times 10 to the negative 27. Is that right? No, 25. I said negative 27. Negative 25. All right. So I hope you can see here that all of these examples are pretty straightforward using the de Broglie wavelength and formula. I hope this video helps you better understand this topic, and good luck.